In the previous two sections, we introduced two types of masks, a causal attention mask and a dropout mask. Now let's actually add those masks to our compact self-attention class, which brings us one step closer to completing the engine of the LLM, the self-attention mask that we are going to use when we are training the LLM. So let me copy this one. This is our self-attention class here. And I think I just saw also a little mistake here. So notice that we have an X here and we have inputs here. So this should also be X. And yeah, speaking of inputs, let's now also work with a batch of inputs. So that would be similar to the output that the data loader in chapter 2 returns. So inputs again is a tensor we had consisting of 1, 2, 3, 4, 5, 6 input tokens, and each input token consists of a three-dimensional vector. Now, to create a batch, just for simplicity, I'm going to just stack two inputs on top of each other. It should probably be across the first dimension. So to give me a batch of inputs, let's call that batch. And this should now, if I didn't make a mistake, be a 2 by 6 by 3 dimensional tensor. Let's see. So it's 2 inputs, so 2 times the inputs tensor. And each inputs tensor has 6 tokens, and each token has a 3-dimensional, or is a 3-dimensional vector. So now we are going to work with this batch. Next, let's make a few modifications to our class here. Let's also call this causal attention. And we are going to add now the causal attention mask and the dropout mask. So let's add a dropout mask here. And then we are going, so this is the dropout rate. And now we are going to add the dropout layer. And then dropout, which uses the dropout rate. Next, we are going to implement the causal mask. So I'm just copying it here. And so the causal mask here is similar to what we have defined before, except that I'm going to register this now as a buffer. So let's call this just, for simplicity, mask. And why am I doing this? Register buffer. Why am I doing this is in PyTorch, we could optionally later on train a model on the GPU. You don't have to, but if you have a GPU, later on when we define the model, we can move it over to a device, for example, a CUDA GPU device. Now, PyTorch will move over all the weight parameters, all the layers here, but it won't do that, for example, for arbitrary tensors like those. And by the way, I define the context length here as the size of the mask, so I should also ideally put that here, context length. So PyTorch doesn't move over tensors like that, so we have to register those tensors, and this is called register buffer. And then if we do that, this mask also gets moved over to the model. And we could technically also generate the mask on the fly here, down here. It's just, a design decision so that we don't have to regenerate this mask every time. We're just generating one mask once with a maximum supported context length. And then we are going to reuse that here when we apply the causal attention mask. So let me just copy and paste the relevant code. So this is just a small update here. So notice that I added a few things. I have now this masked fill now. And in PyTorch, by convention, everything that ends with an underscore is an in-place operation. So in-place means it doesn't create a copy as an intermediate value. It's as if these operations exist, it's a efficiency thing. So, but nothing to worry about. This is just like a small note here that this will happen in place. So I don't need, for example, I don't need anything like this because it already happens in place. So I don't need to assign anything. This will already modify this existing attention scores. And then we have this bool thing where it's applying the mask to those that are non-zero. So we apply the mask, the minus infinity mask that we defined in a previous section here. So we are going to apply this one. So we are setting we are setting those minus infinity values, and then we are applying the softmax function to scale it, and then we apply dropout. So essentially what we are doing is we are applying this mask to our attention score. So it's exactly the same thing that we have here. And then after that, we also apply the dropout mask to our attention weights. So we apply two masks, the causal mask and then the dropout mask. And then we compute the context vectors similar to what we've done before. So let's actually see if I didn't make a mistake. And let's modify this here, causal. I have a few more inputs now, the context length and the dropout rate. So we can define dropout. Let's just set it to 0, by the way, because like I mentioned before, it's not commonly used anymore anyways. And then context length, this should be depending on the batch input. So our batch has 6 input tokens. So let's say our attention mechanism supports up to 6 input tokens. So I can do shape 1, where 0, 1, it should give me this 6 here, as you can see. And let me add white space here, and then we can call it on our batch here. Maybe, let's try it out. Unmatched, I think I have too many of these. Num tokens is not defined. So one more thing I should probably add is I should define num tokens. So we can here, for example, define the batch size, num tokens, and then the input dimension based on our input. So this is 2 in our case, because our batch is 2. Num tokens is 6. And this would be the dimension for the embedding, so the input embedding. So, oops, yeah, this works. So I actually wanted to make a new line here, sorry. So this comes from X, which is batch in our case. And this has, it's a 2 by 6 by 3 tensor, right? So this is, we are just extracting out these dimensions here, but in a more general case. So instead of hard coding those, we extract them directly from the input that goes in here. Okay, and as you already saw, this works. So now we have this causal attention class, which is a nice compact causal attention class to compute the context vectors. So you can see there are a bunch of things. This thing is similar to this thing, and that is because if we look at our batch, we duplicated the inputs. So just for simplicity, this is the first input, and this is the same thing because we created the batch by duplicating it. In reality, when we are using our data loader later, of course, they will be different. So different inputs in our batch, but this is just for educational purposes. And then for each 3-dimensional input, we now have a 2-dimensional context vector. So for the second input, this would be the corresponding context vector and so forth. So we have now a nice causal attention class.
Get this book at Manning.com.